Welcome to the chapter on combustion turbines. This chapter is going to be a little bit more brief compared to some of the other ones, but I didn't want to exclude it altogether. Combustion turbines are something that has some importance in the area of energy, so I wanted to be sure that we cover this material. So it's a quick intro. Gas turbines were developed for aeronautical applications around the time of World War II. So in the decades following World War II, the gas turbine engine became important in terms of propulsion system for most aircraft. But at the same time, the inherent complicity, at least compared with some other primary movers and operational characteristics of the gas turbine engine, resulted in its adaptation for other uses such as power generation and also marine propulsion. So combustion turbines are useful in terms for example, they're used for peaking, also base load or backup and emergency power, and also for various grid-independent power generation. And also it's useful as power sources for remote or isolated facilities, for example, offshore drilling platforms. So when it's used for electrical power generation, combustion turbines basically are operated in two modes. One would be electric power generation with no heat recovery, and another one would be electric power generation with heat recovery. So the latter, electric power generation with heat recovery, is called CHP, or combined heat and power. The subject is covered in your textbook in chapter 11, although we are not going to be covering that specifically. CHP is often referred to also as cogeneration. So the recovery and use of thermal energy in conjunction with the decentralized generation of electricity. So this chapter basically develops the principles for combustion turbines, which is an extension of things that we have done in thermodynamics and topics that I believe you have also covered in advanced thermodynamics. So here's a basic schematic of a combustion turbine. This is also what's called we'll go ahead and look in the simplified version, which is called a Brayton cycle. But here's a basic combustion turbine schematic. You have here a compressor. So you have air coming in, usually at inlet air, just whatever atmospheric air conditions are. They come in, they get compressed, come out of state 2. They go into a combustion chamber, and a fuel is burnt in a combustion chamber, and that increases the temperature. The gas comes out of the combustion chamber and goes into a turbine, and that turbine goes ahead and turns a power turbine, and the combustion gases are then exhausted to the atmosphere, and then the turbine itself is used to power the compressor. And so what you end up with is some net work coming out of the power turbine. Now, as we covered in thermodynamics, and I know that you also covered in advanced thermodynamics, is the simplistic, a simple form of a combustion turbine, which makes it more easily analyzed. It's called a Brayton cycle. So what a Brayton cycle does is that it takes the combustion turbine and it basically goes ahead and does the following. So in a combustion turbine, what you have is that you have hot gases being exhausted, right? So you have the combustion gases that come out of the combustion chamber, they go into the turbine, and then after they drive the power turbine, it comes out as exhaust, right? And so we all know that this exhaust gas is going to be hotter than the gas being taken into the inlet of the compressor. So instead of having this air reject and air inlet here, what we do is that we replace that whole rejection process to a heat exchanger, right? So now we have a heat exchanger where the hot air coming out of the turbine goes through a heat exchanger, rejects a certain amount of heat to the environment, and then that brings down the temperature of the gas down to what the inlet conditions of the air is. This is, again, just to make it more analytical, easily analyzed. And likewise, for the combustion chamber, instead of having fuel come in and burn, what we have instead is a Q-in process, right? So we have a Q being added to air that increases the temperature of the air from it's higher coming out of state 3 than it is going into state 2. So, and again, it's a constant pressure process, right? So there's no actual increase in pressure, but there's a huge increase in temperature since heat is being added to the combustion chamber. So this is what the Brayton cycle ends up with. You end up with a process that, a cycle that kind of looks like this. So we have again a compressor going into a heat exchanger, coming out in a turbine, and then the air goes through another heat exchanger. So here you have work in, here you have Q in, here you have work out, and here you have Q out. And so the ideal Brayton cycle basically splits up this cycle into 4 processes. So we have process 1 to 2, again, which is the work in process, and again on a TS diagram that would be represented as an isentropic process. So we say that process 1 to 2 for the ideal Brayton cycle, we call that isentropic compression. And then here, the heat in process, right, basically is the combustion chamber replaced with a heat in process. It is called constant pressure heat addition. So again, this is a heat addition process with constant pressure. And then process 3 to 4 here would be what we would call a work-out process. That's a work-out process from the turbine. So that would be isentropic expansion. And then lastly, here we have, instead of just air being rejected to the atmosphere from the turbine and atmospheric air being taken into the compressor, we replace that with the Q out process. So that would be process 4 to 1, which would be considered heat rejection or at constant pressure. Now, one other thing too that helps make this a little bit easier to analyze in terms of assuming a Brayton cycle is that air is the working fluid the whole time, right? So you have air being compressed, air being heated up, air being expanded, air being cooled down. Whereas, and it's all air without the composition of the air changing. Whereas in this power cycle, in the real power cycle, you have inlet air coming in, so you have air coming in, then the air is mixed with fuel, and then the air comes out as combustion, combined with combustion products, and it gets rejected to the atmosphere. This is a closed loop cycle where all the air is basically encapsulated in the cycle, right? It's inside the system, and the composition of the air is not changing, just the properties of the air due to pressure and temperature changes. So another thing I'll highlight is that, again, I'm going to go into a little bit of detail, but just a quick review. If we were to do a first law analysis on any of these cycles, let's say for example, let's look at, I don't know, the turbine process, right? Here's the expansion process, right? So for the turbine process, if you were to do a first law analysis where we have the rate of energy in minus the rate of energy out equals the rate change of energy of the system, you would say, okay, the system is steady state, so there is no change in energy of the system. So you have energy in, which of course would be by mass. So we have the mass flow rate at state 3 times the enthalpy at state 3 going in. Has to equal the energy out, right? So when there's no change in energy of the system, you have E in equals E out. So E in would be by mass, and E out would be by work and also by mass. So we have that the flow rate in is equal to flow rate out, so that m dot 4 and m dot 3 end up just becoming m dot because the flow rates are equal to each other going in and out. So what you end up with is this first law that results in that the energy exchange term, the work term, is equal to basically the difference in the fluid energy going in minus going out, H3 minus H4. And so basically what I'm saying is that you'll find that same result for any of these cycle processes, right? So for example, the heat in process, well, you have Q in. If you were to do a first law analysis on this, you get, well, energy in by mass plus energy in by heat equals energy out by mass. So you end up with the Q in is equal to the mass flow rate times the change in enthalpy of the air entering and leaving. You would find the same thing for the compressor, that the work in is going to equal mass flow rate times the change in the enthalpy entering and leaving, and the heat out is going to equal mass flow rate times the energy change in a mass entering versus leaving. So what's great about this process is that what's great about this cycle and this assumption is that each of the analyses, first law analyses for each of the cycles, end up becoming basically the same thing in terms of that the energy term is going to equal the change in energy of the fluid entering and leaving. If we're going to look more specifically into that, we can actually maybe hammer out a few more details concerning that. Let's look at the two, for example, let's look at the two isentropic processes, right? So we have two isentropic processes going on. We have process 1 to 2, which is the isentropic compression in the compressor. And then you have process 3 to 4, which is the isentropic expansion in the turbine. So again, if we were to do a first law analysis on each of those processes, we would get for the compressor that the work into the compressor is going to equal the mass flow rate times the enthalpy out minus the enthalpy in. And then for the turbine, we would have that the work out of the turbine is equal to mass flow rate times the enthalpy in minus the enthalpy out. Now, if you remember back in thermodynamics, there's basically a few ways that you can handle quantifying this or simplifying this even more. So when you're dealing with an ideal gas, which is what air is, which is what the working fluid of this is, in order to evaluate the change in the enthalpy, right, we can assume either constant or variable specific heats, right? So if we go ahead and if we assume, and if you guys don't remember what constant or variable specific heat is, I would reference you back to chapters 5 and 7 in your thermodynamics textbook. But if we were to assume constant specific heats, basically what that means is that my specific heat is not a function of temperature, right? And so if you remember, back in thermo, we get that basically enthalpy can be, not enthalpy, but specific heat at constant pressure can be referred to as the change in the derivative of the enthalpy with respect to temperature at constant pressure. So if you were to actually go ahead and evaluate this integral, right, we would basically end up with, if you were to actually algebraically separate out the enthalpy, you would end up with dH is equal to Cp dt. And then if you wanted to actually compute what H was, you would have to integrate both sides. And this integral here would have to make one of two assumptions. If I assume that the Cp, that the specific heat is constant with temperature, I would get that delta H is equal to Cp delta T. If not, I would actually have to integrate this, right, and assume that this specific heat changes with temperature, which it actually does, but when you have small temperature changes, you don't have to really, it doesn't really change that much, so you can assume it to be constant most of the time. But if you wanted to actually take into account the variable, the fact that specific heat changes with temperature, you would have to actually use the thermodynamic tables and compute what the enthalpy at each state is by using the ideal gas tables, right? Where the ideal gas tables basically give you enthalpy as a function of temperature, taking into account the specific heats actually change with temperature. So I hope that kind of brings back memory a little bit from thermo, but we're going to be concentrating basically on assuming for these Brayton cycles that our specific heat is constant with temperature. So with that said, you can come back to, I'll go ahead and erase these since I don't really have a lot of room in these slides. Give me a moment. So assuming it to be constant at specific heats, I can go ahead and I can factor out my specific heat, and I can get my work in and work out in terms of temperature. Now, the next step in this is that this is an isentropic process, right? So what we want to do is that we want to find a way to quantify the temperature change, assuming this thing to be 100% efficient, right? That's what isentropic process for a compressor or turbine means, is that it is operating at its highest possible efficiency, not producing any entropy. So if that's the case, then I'm going to make the assumption that this is, again, an ideal gas with constant specific heat and isentropic process. If that's the case, then assuming those, if you go back to your thermal books, we can go ahead and we can say that the temperature coming, for example, out of the turbine or out of the compressor divided by the temperature entering the compressor is going to equal the pressure ratio to the K minus 1 over K. And again, that's for an isentropic process. Same thing for the turbine. The temperature coming out of the turbine is going to equal the temperature divided by the temperature entering the turbine is going to equal the inverse of that pressure ratio to the K minus 1 over K. And again, that is for a constant entropy process. Right, so that would be what's called the isentropic work in and the isentropic work out of the turbine. So this pressure ratio across the compressor and across the turbine have a significant effect on the amount of the efficiency of the process. Right, so if we actually progress to the next slide, you can kind of see that basic graph here that looks at, on the y-axis here, we have the efficiency of a Brayton cycle or combustion turbine as a function of pressure ratio. So as the pressure ratio increases, you can see that the efficiency increases, although the advantage decreases as the increase in efficiency goes down a little bit. The rate of increase in efficiency goes down as the pressure ratio starts advancing past 20. Okay, I hope that helps. We're going to I'm going to take this one step further, and I'm going to actually take this. So again, these are for what I would call the isentropic, right? So this is for constant entropy or isentropic work. So actually, we would signify isentropic work by putting a little is there as part of the subscript. So isentropic work for a compressor, isentropic work for a turbine. But actual processes, an actual gas turbine process won't actually have isentropic compressor or an isentropic turbine. So we have to actually take into account compressor and turbine efficiency, right? So I'm going to split this slide up into two different parts. I'm going to just basically quickly cover and review. This is a review because we did do this in thermo. A review on how to handle the efficiency of a compressor and the efficiency of a turbine in terms of cycle efficiency. So again, this is not the cycle efficiency. This is the efficiency of a turbine or of a compressor, which is basically saying as the turbine becomes, as a compressor, I keep confusing the two terms, please forgive me for that. But as the compressor becomes less efficient, you have to put more work into the compressor to get the same pressure difference, right? To get the same pressure increase. So we would say that the efficiency of a compressor would be the minimum work or the isentropic work divided by the actual work, right? And for a turbine, it's the opposite. As the turbine becomes more inefficient, you get less work out of it. So we would say that the isentropic efficiency for a turbine is the actual work divided by the isentropic work. So we can actually expand this, right? So we get that the isentropic work for the compressor is mass flow rate times the change in enthalpy. So it would be H1 minus what I would call H2S. H2S means the enthalpy coming out of the compressor if the compressor were isentropic. That divided by the mass flow rate times the enthalpy in minus the actual enthalpy coming out of the turbine, of the compressor. Here we can go ahead and we can cross out our mass flow rates. We assume constant specific heats. We can factor out the specific heat. And again, assuming that we evaluate the specific heats at the same temperature, which is what cold air standard assumption says, is that the specific heats are all evaluated at room temperature, we can get the isentropic efficiency of the compressor to be solely a function of temperature. All right, so again, this is the temperature entering the compressor. This is the temperature exiting the compressor if the compressor were isentropic. And then this would be the actual temperature exiting the compressor. The same thing for the turbine efficiency, right? I get mass flow rate times the enthalpy going into the turbine minus the actual enthalpy coming out of the turbine divided by the isentropic work, which would be the enthalpy going into the turbine minus the isentropic enthalpy coming out of the turbine. Mass flow rates cancel out. I can go ahead and assume constant specific heats, factor out my specific heat, assuming that they're evaluated at room temperature. I can just go ahead and also cross out my specific heat and get my turbine efficiency as a function of temperature only. And again, as you can see, this is the actual temperature coming out of the turbine. This is the temperature coming out of the turbine if it were isentropic. Basically, what you can do is that you can use the isentropic work to evaluate, and if you have the turbine efficiency, you can evaluate the actual work coming out of the turbine. So if we were just to actually, what we'll do is that we'll actually stop the video here, and what we'll do is to pick up on a few example problems in the following video. So this concludes video number 1 for the chapter on combustion turbines.